the Very Large Array, and RFI Mitigation from Adam Kimbrough. N4 ADK, starting now. Welcome to Ham Radio 2.0, guys. My name's Jason. I'm KC5HWB. If this is your first time here with us today, please click on the subscribe button below so that you can keep up with all the videos we post on this channel that answers the question, what is new in amateur radio? Today, we get to hear about the Very Large Array, and I admit that I didn't really know what a Very Large Array was, but it's a huge satellite dish that listens to space on radio frequencies. It does a lot more than that, but that's a very rudimentary description of it. So Adam Kimbrough, N4ADK, gives us a presentation on how to mitigate RF interference and what the Very Large Array is, and we get to see a lot of pictures of it. This was very interesting. If you're into radar or space communication at all, you're going to enjoy this topic. Stay tuned.
So I'd like to introduce Adam Kimbrough. Did I get
yeah.
that correct?
Mm-hmm.
N4ADK. His talk on the Very Large Array and RF mitigation.
All right. I'm Adam Kimbrough, N4ADK, and I am from Richmond, Virginia. I just did my first year of college this past year at NC State, and I'll be at Virginia Tech this spring. But in between that, I have the dream opportunity to work at the Very Large Array for 6 months. I'm living in Socorro, an hour south of here, which is an hour east of the VLA. And I'll tell you about the Very Large Array, and my specific job is to help mitigate radio frequency interference by doing a bunch of different things. So, a little overview with some radio telescopes. So we have the single dish, Green Bank being the most known, and then in the largest fully steerable single dish, it's about 100 meters diameter. And then we have arrays, which can be phased arrays. In our VLA case, the interferometer, and we'll talk a little bit about that. And there's no one's better than the other. I mean, they can do some small differences with their resolution capabilities. So some benefits of observing with radio. You can track these physical processes that you wouldn't see otherwise at different radio wavelengths. See through dusty regions, magnetic fields. Definitely something we can learn about through radio. Line of sight velocities, perhaps one of the biggest things that radio astronomy has told us is we have the CMB, cosmic microwave background radiation, verified the Big Bang, and we saw that one side of the universe is cold, the other is hot, and from that we could get the velocity of the solar system at, from what I understand, a pretty accurate number of 370 kilometers per second. So, and then of course, daytime observing can't do with optical. Yeah. Some more overview here. So there are 28 antennas, one spare, 27 are used. At least when not one of them has some maintenance. And fully reconfigurable. We move them around. We have 4 configurations, A, B, C, and D. Right now, we're in the D array, and that's what you see there, the closest. And that's going to give you the broadest view. As you get farther away, you get more precise look at whatever the object is. So we're at about 2,100 meters, just under 7,000 feet. Desert climate, pretty dry except for the monsoon season, which we're just coming to the end of. We get daily downpour at around 3-4 o'clock. And so yeah, that gives us a really good advantage of observing. For example, K-band, I'll get into the frequency bands a little later, but K-band is really good in dry conditions, and that's what we were observing this past Friday. So yeah, and of course, I believe we're about a third up in the atmosphere, you know, so we have less to get through or to receive from. Yeah, and then so we have the VLA site. We also have the DSOC, the operations center, and that's critical for all the science. That's where the science happens, and then engineering is going to be at the VLA site. But we do have a lab in the basement of the operations center where electronics are built. A big upgrade in 2012. We'll talk about $94 million. Lots of electronics upgrades. So the resolution, just a little bit here. So with an interferometer, you're going to use pairs of antennas, and each of those pairs are cross-correlated with our correlator at the site. And with a dish, obviously, you've just got this one surface. So if you have a 100-meter single dish diameter, it's going to have the same resolution as if you had these a pair that was 100 meters distance apart. So the single dish and the arrays are going to have a little bit different kind of resolution. I don't know too much about that, but yeah, that's and as far as the configurations go, the D array is about a 1 kilometer distance away, and then the A array is 36 kilometers distance. So they're 25-meter paraboloids, off-axis Cassegrain Design. This is unlike the Green Bank, Arecibo, and some others. Those are Gregorian. No real benefits or negatives between the two. It's just the fact that we have, with the Cassegrain, you have a convex subreflector, the thing that's sticking out from the dish. Convex subreflector looking at the concave main dish, and with the Gregorian, it's a concave looking at concave. And we change the bands, the frequencies, by rotating that subreflector. Visual there. So you can see all of the 9 bands, feed horns at the bottom there, and the radio waves are directed through, bounce off the subreflector into the feeds. Yeah. Little image of size here. Picture of me on the right earlier this year. Yeah, they're pretty big. Okay, so just some numbers I'll go through a little bit. These are upgrade numbers as far as technical capabilities of the EVLA, as we'll call it. It's an expanded very large array, interchangeable. You can call it VLA as well. JVLA, Jansky VLA, was the previous name. So source. So with the sensitivity, we're talking about Janskys here, micro Janskys, and that's going to be a watt per meter squared per hertz, and we had a 10-factor increase in the upgrade. Bandwidth, pretty important. We can get up to 8 gigahertz maximum bandwidth, each polarization. So with the VLA, normally it's looking at 2 different frequencies, but it can look up to 4 frequencies at once. And for each frequency, you have the left circular polarization and the right-hand circular polarization. For each polarization, you can do up to 2 gigahertz of bandwidth. So if you have 2 frequencies, So you can get 4 from each frequency. The channels, lots of channel increases as far as specifically looking at frequencies. Yeah. And the VLA looks at 1 gigahertz to 50 gigahertz is that range. Previously, 22% of that range is what we were looking at, but in 2012, once we started upgrading these dishes, we got up to the full range. So we have different bands, and we call them by letters. I remember one visitor, I was eating lunch outside, and we started talking about some of the technical things, and I started throwing out these letters, and he was like, he almost got upset. He was like, just give it to me in the frequency, the number, but yeah, it takes a little while to get used to. So yeah, we have the T-sys, that's the system temperature of the receiver, the antenna, and I think there's one more thing, but yeah, it's going to be in Kelvin. So as we get up to Q band, it's going to be a little bit more. And yeah, there's a good image of our feed horns. And I'll show you some modules here. And we had a power upgrade recently, and over a month without power. And this was towards the end, and somebody just couldn't find a long Ethernet cable, so just dangling that. But yeah, those are in the background, all the EVLA modules, down converters, and all of that. Closer look here at the samplers. So we have an 8-bit sampler and a 3-bit sampler. We'll use the 8-bit sampler for this lower frequency L band, 1 to 2 gigs, and the 3-bit for these higher frequencies. And of course, we have a huge fiber system that runs beneath each of the three legs of the VLA. And of course, this upgrade was, we went from analog electronics here to digital. So more about the receivers here. Remind you of what these ranges are. And yeah, this is the Vertex Room. That's the top level of the Vertex Room of each antenna. And they're all cryogenically cooled with helium. And that keeps the system temperature down, so we can have as much noise floor, because we're trying to look at these signals out in the universe, and we keep it at around just several Kelvin, so it's pretty impressive. And then the lower level, we have the bigger feed horns, the L band and S band. And we keep some spares, of course, so that's how many receivers we have. In addition to these high gigahertz ranges, we also have a low band system, and what that is, we have P band and 4 band is what we'll call it. I think you'll see it a little bit later, and the P band is a cross dipole. That's on the right there, and that is that's still, it says old, but it's still used for P band, which is 327 megahertz. That's, I guess, the middle of it, I believe. And then we have the 4 band system, 55 to 85 megahertz. And what we used to have before, these are what we call MJPs, modified J-poles. Some I don't think it was a student, but oh yeah, I should have. Yeah. So someone made this design that was like a J-pole, but they basically extended the smaller portion of it, and we've got 4 of those in a box. And what was previously used were just dipoles, wire dipoles for 4-band, but these got much better return loss measurements and for this frequency range that we're looking at. And these are used 24/7 with V-Light, which is a separate. I think I have a no. It's a separate program that's just dedicated to low band that we use. I think about 10 of our, at least 10 of the antennas are always giving information to that program. Yeah, it's a commensal program for the Naval Research Laboratory. So now we'll just look at a little thing of RFI spectrum here. This is going to be, yeah, this is a P band. And yeah, it's surprisingly not too bad. 2/3 of it is usable. But we have these things, we have satellites, mobile user objective system, which is what military satellites are using. But good portion of it is good. We'll look at it closer. So I'll tell you about the correlator now, given to us by the Dominion Radio Astrophysical Observatory in BC, Canada. It's quite a beast. There's some numbers here, 170 kilowatts of power, yeah. Lots of FPGAs. And yeah, actually a large amount of our operating cost is cooling this thing. So yeah, it's very important. It's a very sensitive supercomputer because we had the power outage. This was a power system upgrade to go from 2 generators that we were using to 1 generator of a lot of power, a couple megawatts. And in the transition, we expected that some things would break in here, and that would increase the time of recovery. But we are back up now. So we'll look here at is this L? Oh yeah, yeah, L band 1 to 2 gigs. So we have lots of aircraft navigation RFI that we have to look out for, satellites, cell phones. Yeah, and you could see the dips where our digital filters are cut off. Can't remember what type of filter that is. Yeah, we'll look at more graphs later. So now just tell you about some of the sources that give off radio waves in our solar system. The sun that we will look at, planets, Jupiter, we'll see, galaxies, we got magnetic fields in them, neutral hydrogen is a huge thing that we look at, and yeah, like I said earlier, CMB, cosmic microwave background radiation also. So looking at the sun, we see 3 different frequencies, different levels of what's coming out, 5 gigs, 8 gigs, and 11 gigs. Jupiter, something that I worked with a few years ago in high school. I did this project that it's like a NASA project called Radio Jove, super fun, where you build a receiver and a dipole array, two dipoles connected together, and you can receive Jupiter's electromagnetic radiation. Not shown in this image would be Io, one of its moons, has a pretty big influence on where it sends out its radiation, and that's going to be cyclotron radiation. And of course, Cassiopeia, we have, which is a supernova remnant, and that image, VLA image, combining 1.4 gigahertz, 5, and 8.4. Also synchrotron radiation. All right, so we'll get into RFI detection and reporting, my job and some of the things I do here. This is the latest edition of Microwaves in RF. Seriously? Radar revolution? Radar. Really? Okay. Apparently the biggest enemy of the VLA is itself, which is true. Which is true. We have a lot of RFI. So these are protected bands, and we have small slivers, but as you can see, a lot of because we go up to 50 gigs, a lot of it is shared with other people, and we shouldn't expect any RFI in these areas, and for the most part we don't. But we have all this to share from, and you can imagine it's kind of hard when you talk to the FCC or actually the NTIA for federal communications. When you tell them we need this band, we're not gonna use it at all. We just want to receive with our super sensitive receivers. So yeah, it's kind of hard to sometimes get these allocations. So example of one thing I've done this. I'm at the halfway point now, 3 months on the job here, and we go up to radio sites. This is Davenport Lookout, which is probably about 30-40 minutes further west from the VLA towards Daddle, and we'll go up there, and basically the objective is to point antennas at these towers and make sure that no one has added any other transmitters we shouldn't know about. So here's some intentional sources. What I mean by that is these are the ones that we can coordinate around. We have monthly meetings and lots of email exchanges with Air Force bases, and to make sure that when they want to do testing or whatever, we make a note of that. Lots of aircraft. Radars. We'll look at graphs in a minute. And Columbia School, they've got scientific balloons that we have to look out for. I think they just launched one recently or coming up that we'll have to make a note of. Continued, more weather things. We have wireless car keys around 315 megahertz, which is pretty cool to listen to if you ever just want to get SDR and just listen to see what yours sounds like. It's pretty weird. But yeah, especially cars though, we're getting into self-driving cars. It's going to be more of an issue, so we'll have to look out for it. Lots of satellites, communication satellites, Iridium, they've got their new constellation that's being brought up. So we're always looking at that. And then I guess in terms of RFI, in the sky, the brightest star, if you will, is Sirius. They have a geostationary, and then they've also got ones that are going around. So that move. And here's a look at a graphic here. You can see some satellites in the middle there. On the left, on the far left, you have two lines. The most left one is the interrogator of aircraft, which is constantly pinging planes. And then on the just to the right of that is the plane's response, a little more higher power there. And yeah, you can see how around 6 a.m. it picks up on there. And then, yeah, if you see right there, we have the VLA radios, second harmonic. That'll definitely show up. We actually had, believe it or not, Motorola radios that we used to use. You know, great company, but those were giving RFI at the 11th harmonic. So, I don't think I mentioned it later, but as far as our radio situation now, we're using Baofangs and Kenwoods, but what we do, instead of buying a bunch of Kenwoods that are super expensive, we're just buying these Baofangs for $30, but what we do is we add a filter between the antenna and the radio. It's about a couple inches long, costs $60, so we're saving a lot of money doing that way. Of course, we don't want workers to use the site radios when they don't have to. We have a VoIP phones out there at each antenna, so they don't have to produce RFI. The RFI that would be with these site radios is the P band, which we actually try to keep studying it at night and not the daytime. So, but sometimes we will. Okay, so unintentional transmission sources. These are things that produce RFI just because that's how they are, and we have to still look out for them. Cell phones, radios, the broadcast stations, digital TV. And yeah, our local oscillators will leak. There's problems with that, but I'm sure they try to keep on top of it. Yeah, as I mentioned, the site radios, crazy harmonics. Yeah. So digital electronics, of course, are always going to produce things. The monitors, so that's one thing that I work with, and what the VLA is always doing is we have to shield our monitors, and we do it a special way. We will basically cover it in copper tape, specific parts on the inside. We will take out the AC input and replace it with a filtered AC input. We'll put a screen over it, see-through screen for the display, and we'll distribute those at the site. As far as like the computer itself, we don't at this time put them in any sort of box Faraday cage. So that might be something we do in the future. Yeah. Motors are a big thing. So common characteristics between these, they can be intermittent or varying strength. So like radar is going to be very spotty. And of course, when you're trying to look at that on a spectrum analyzer, it's like you kind of got to get your sweep time. You got to keep adjusting, and because you could be missing it every time. So you're usually spectrally limited except for ultra wideband stuff. But we will see that through the T304 module, which gives us this total system temperature for the bands. So what do we need to know? We need to know the frequency, the bandwidth, strong or weak relatively. When are we seeing it? The duty cycle. And where is it pointing, like these satellites? Because the last thing we want to do is point the antenna directly at the satellite. That would damage a lot. So we have these monitoring stations. We've got 3 on site. Well, actually, really 2. The RF EMS and DFS are in the same shelter, as we call it. I've shown pictures of. It's a little shelter just out, probably a couple hundred meters out of the main control building. And yeah, we do 24/7 monitoring of different different bands. At the for the RF EMS, right now we've been looking at 2.4 to 3, something like that, and that's going to be where Bluetooth is and Wi-Fi and that. So the DFS, direction finding system, that's what that antenna is in the top right. We'll use that when we need to pinpoint some things, whether that's on the site or outside of the site. That's how we find people who have left their Wi-Fi or Bluetooth on for a long period of time. We'll actually try to find them and tell them to turn it off. So you can run, but you can't hide. And then the W8 monitor is in the control building, and that is tapping off of, actually, I think I started to talk about it in a second. MK at Mauna Kea, we have access to that remotely that will make sure it keeps running. So yeah, this is an EMS, RF EMS plot. You can see Wi-Fi channels here. You'll see Bluetooth hopping around on its different channels there. And yeah, that's right here, Wi-Fi. Somebody's leaving on for a pretty long period of time. And oh yeah, so this is what our plots we generate look like. That's a 24-hour plot, grayscale from a while ago. And then this is the bottom, just showing you scale here, dB scale and resolution, bandwidth. And these, so that's peak hold. It peak holds for 1 minute, and then resets and does it again. Okay, so I should tell you about the W8 monitor. That is, so it's in the control building, and it taps off of the RCP of one of the guest. I don't know what it's called, like the antenna that people can walk up to. Taps off of that receiver and also the P-band antenna. We look at frequencies there. Okay, so now I'll tell you about the RF chamber, reverberation chamber that I spend a lot of time in, running tests for monitors. At the very beginning, I did a new rack, electronics rack for the VLBA system, which I'll talk about. So yeah, this is our reverberation chamber. And first I'll tell you about a couple different types of testing environments. We have the open area test site, or I guess we call it the outdoor antenna test range, OATR, and that is that's right to the west of Tech Campus. In front of the M Mountain there, and I did we did a 40 gigahertz feed horn test there that my advisor Dan Mertley was I guess contracted to do a little while ago. We have indoor acoustic test range. We don't have this. I just wanted to mention that is one type. That's not going to have reflections or as much as what we use, which is the reverberation chamber. So our outdoor antenna test range here, advantages, I mean, you get real results here out in the environment, free space ideal. So, you know, there is RFI from whatever else is out there that you can't really help. Dust and wind, you know, getting in the connectors, it's a problem. It's also really hot in the summer when you do this. So, yeah, and it takes a while. It takes several days for testing setup. So the reverberation chamber here. So the picture there is a stirrer, and that is what we use. We spin it 3 times, 120 degrees each time, and average these results that we take in from our antenna that I'll show. And we want the maximum amount of reflections here, and then of course, higher sensitivity you'll see we have to block near field radiation. So yeah, the main objective here is to disperse all of these radio waves around so you can get as accurate as possible. Emissions test. We do 2 types of tests in this thing. We do emissions tests and shielding tests. Shielding tests being making sure that this equipment is okay to put in the Vertex Room and on the antenna, or even in the control building, 100 meters away from the nearest antenna. So a disadvantage, you do have to calibrate this thing. You'll see a bunch of junk in the room, but that stuff stays where it is, so it's fine. But you have to calibrate all of that, which we do every 2 or 3 years. And that'll give us insertion loss, and we can take that out with these equations for our Excel spreadsheets and when we plot the results. So transmitting antenna, that's the one side of the chamber there. We keep everything in this red tape box. I think that image is probably when they were doing maybe a calibration, because I think they point the antenna into the corner to maximize reflections. But yeah, we'll usually have a table there, and that's where we set the device or equipment under test, the EUT. This is the Pomeroy antenna. Pomeroy is one of my advisor's summer slaves at 1 year, and he designed that antenna. It's a biconical UHF antenna. We're always using that. And then right here we'll have 2 LNAs. We have the low band LNAs for 0 to 1 gigahertz, and then we'll use some other mini circuits LNAs for 2 to I guess up to around 6 gigahertz usually. And then the mode stirrer. So we don't have any modes like I guess visually like a ball of RF in one corner of the chamber, so we want to disperse it. Pictures of the feed-throughs. We have to filter everything there. VGA, DVI, stuff like that. We're testing the monitors. And that long pipe there is fiber. Previously, they just did fiber like the other feed-throughs, but this long pipe helps cut down the other wavelengths we don't want. And yeah, we wrap tinfoil around certain cables as well. Here's an example plots that we'll get from one of these tests. This is a unmodified Dell monitor that we use from 0 to 1 gigahertz, which is where it's going to be noisiest. And yeah, we got some wideband stuff from it. Could be like the display seeing if it needs to go to sleep or something like that. And we're at around minus 120. So then when we plot it, we also, that's the raw plot, and then we take this, which is the threshold, the dotted line threshold, which Rick Purley has a memo about where he does the calculations for the detrimental threshold for Vertex Room and also control room. So yeah, that's still unmodified, but I don't have the modified picture with me, but it's going to be all below that line. And sometimes we'll look at 1 to 2 gigs as well, but usually the monitors will not to go in that area. I should go back, also mention with the chamber, you might expect that this mode stir here would produce a lot of RFI. Well, it does, but we turn it on, we turn the power strip on, turn it, and then turn it off. So otherwise, the whole 0 to 1 gigahertz is noise floor is huge. Okay, so just talk about a few different antennas that are around there for radio astronomy. So right now we have EVLA, which has been made very much better in 2012 is when that was completed. We're still, making some additions to the antenna, like the low band system. This past week, I just replaced the second to last dipole with the modified J pole for the square thing. We have one more to go for that. ALMA is, it has a lot more antennas. It's very much has better resolution, but that's going to be for sub-millimeter. ATA, the Allen telescope array, talk about that. That's dedicated to SETI. LOFAR, and then future we have NGVLA, pretty big thing that we're fingers crossed that the money goes to it. But recently they had the science book, which had a bunch of scientists submit their proposals for what they want to do with this antenna. And SKA, another thing that's in motion. We had some people from their visit last week or a couple weeks ago to look at our RFI stuff and some other things. That'll be in South Africa and Australia is what they predict. So a closer look at ALMA. 16,000 feet up, it's crazy. They actually need some oxygen tanks when they work on it. But they are smaller than the VLA, only 12 meter diameter. So they're not actually like climbing these antennas like we do. They're just using a man lift for everything. It's fully configurable, just like the VLA. And that, like I said, that's sub-millimeter wavelengths. And a great environment for studying. So all of their science that they get, that goes to the Socorro Science Operations Center. Same with VLBA, which is the very large baseline array, which is 10 antennas in the U.S. From Mauna Kea to St. Croix. And those are working as an array together. $1.4 billion, a lot. Here we have Paul Allen funded, co-founder of Microsoft, SETI dedicated antennas out in California. Can't remember exactly where. They have quite a bit of collecting area and should be interesting because it speeds up their ability to search by 100 times from what they were previously doing. So we have LOFAR, low frequency array, proposed in 2008, finished in 12. That is the Observatory in the Netherlands. it says 100 stations with 100 antennas at each, but they actually have 20,000 antennas at this point now. It's pretty crazy. This one, I'll be honest with you, I have researched this, and like, there's not a lot of info out there. Like, I don't know if it's dead in the water. It seems like it, but yeah, this is a solar radio telescope that I would be really interested to see what happens with it. But that has been proposed in 2009, and they might be still working on it. And then we have SKA, which is a very big project. So some conclusions that we make here. We're pretty new into radio astronomy, but as this digital technology is improving, and we have faster speeds, more bandwidth, it enables a lot more studying that we can do. Of course, coming from the engineering side, so I try to make sure I can understand most of the science that they try to do. And yeah, you don't need a well-funded PR machine. NRAO is very well run, and it's pretty impressive. Oh yeah, and that's questions that I'll try to answer. If not, we have the block diagram and the control building.
Hey, can you give me one big factor in the 10x improvement and sensitivity?
Oh, I don't think I can, yeah. I'm sorry, yeah.
I look forward to your arriving in Blacksburg.
I do too. Go Hokies. Awesome. I'm looking forward to it. Yeah.
Have you published or thought about publishing all your little RFI mitigation techniques, like shielding monitors and so forth? I mean, you could put this into a book, and believe me, you could sell it.
Yeah, I've heard, like, just reading like online blogs for like ham radio stuff, and yeah, a lot of people are really interested in this RFI stuff. So
I mean, you obviously have more experience with this than probably anybody. You need to write a book about this stuff. People agree here? I mean, who would buy that book? You get a lot.
There's your challenge. Go ahead, Bill.
The data that's fed from the antennas to the correlator, that's all digital data. It's all digitized at the antennas, yes?
that's correct. Yeah, it goes through the fiber, and yeah, it's all cross-correlated there.
Nice talk. Do you guys at places like the VLA talk about global internet coming from people like SpaceX and Google? Are you aware of what they've filed and what they want to do?
Yeah, we're definitely looking at that, like OneWeb, I think it's called.
Right.
Yeah.
You might want to summarize for this audience, for those people who haven't seen that.
Yeah, it's a huge constellation. Like, personally, my concern about it is the debris, this, possible space debris that can happen with this. But related to RFI, I mean, they're trying to get internet. I mean, you have Internet of Things, which I don't really like that term, but yeah, they're trying to get internet to all these things through constellation satellites. Very cool stuff. But yeah, that's going to make things challenging. Like a decade ago, I mean, I see in the office that I work in, my advisor, he has notebooks of just Iridium, data and meetings and all this stuff. So it's coming, but it's not quite here yet. But we'll have to look at it. Yeah.
The filing is for 2,200 satellites at 600 kilometers orbit within 5 years. That will basically wipe out pretty much everything above 10 gigahertz. permanently. And that's one of 6 companies that have filed with the FCC for licenses. So it's an enormous problem, and we shouldn't just let the folks at the VLA or what have you deal with it. The radio community could possibly help by squawking.
Good presentation. Actually, I enjoyed back in February visiting the site, which I had a blast there. That was if anybody hasn't gone there, go. It's very cool. It's about a couple hours south of here. But I was surprised at the relatively soft sell as a tourist on turning off your cell phone and things like that. I kind of figured they'd not want any of us with all sorts of uncontrolled devices anywhere near the facility. I mean, how do you deal with just tourists? I mean, you invite them, which is great.
So it's not like a law or anything. We have signs, but I mean, we can't force them. Yeah, we can point our huge antennas at them. That might work. But yeah, we make sure that they keep that Bluetooth. And I mean, you could take pictures. It's fine. I mean, you can, but as long as the Bluetooth and the Wi-Fi is off, is perfect. Probably shouldn't say this, but cellular data is maybe okay, but don't tell anyone that I said that.
Well, so one answer to Phil's question is, if you considered turning all of your antennas into high-powered transmitters, then you could just blast the space junk right out. And because if you can't use 10 gigahertz, you could just clear the skies.
There is word about some government contracts with the VLA, so.
Okay, and George, you get him in the back?
Yeah, I will echo what was said about the going down to see the place. Not only do you get to see a fantastic view like that, but the visitor center is very, very well done. It's worth the time down there. And there's an interesting little display with a 7 gigahertz radio telescope that you can play with. So that's kind of cool too. So it's really worth the trip down there, even if you're not a microwave kind of person. The other thing is, if you're even more interested in radio astronomy, there's an outfit called the Society of Amateur Radio Astronomers that is very active, and it's worth looking into. And if you look that up on Google, you can get their website and all that good stuff.
Yeah, definitely.
And thank you for a nice talk. Appreciated it.
Thank you. I should mention also, Skylar did the position right before me. He did the same exact position, and I think he might have worked on that solar radio telescope. We have students work on that.
Okay, one more question.
2 items. One, there may be someone here from the Socorro Amateur Radio Club, but with their Hamfest, the day before on Friday, there's usually a VLA tour for hams that's presented by a ham. I went a few years ago, and it is really worthwhile. You might be able to fill in on the details. The other one, the question though, was when I was out there a few years ago, there was an area about the size of this room that had a bunch of dipoles at knee level or so, it looked like. That I guess was the beginning of the low frequency.
Yeah, that is the LWA.
Is that still there, and is something like that feasible for civilian or for citizens to participate in a network like that?
I'm not sure about citizen participation in the LWA, but yeah, that's just to tell people, that's like, I think it's below 80 megahertz, around there, from like 20 or 30, and yeah, that's a huge space that. Well, actually, now that I think about it, there is talk about having universities get involved with the LWA and having their own, and then connecting all of them, and also with the NGVLA, they might have LWA antennas as well. Those are like disc cone antennas that are about 3 feet off the ground, and then like hundreds of them. Yeah.
Well, thank you very much.
Thank you.